Okay, obviously yesterday we finished up the last topic of the class, and as I mentioned yesterday, um, again, you will not be responsible for chapter 11, which is kinetics on the final exam. Hopefully it would be helpful for you what we talked about next semester as well for your final. Again, they usually have some kinetics type questions on the final and stuff like that. And you do get into some kinetics in that radioactive chapter that you cover usually in 200B. So hopefully that will be helpful. But for us, since we just kind of finished it up yesterday, it's a lot to digest here in one day or so. So we're going to take that off of the final. So really the final, I think, will cover kind of chapters, I guess it would be 1 through 10 then, I guess, in that case. Pretty much everything through the last exam, I believe, should be on there. So what I plan on doing today is just kind of going back to the beginning, believe it or not, and just kind of, hitting some of the main points of these chapters and kind of going through it. And obviously, if you have questions along the way, you could ask. Just going to kind of go off the top of my head on, some of the topics and stuff that we kind of talked about through the semester, some of the formulas and stuff that we used, and hopefully it'll be a good review for you. All right, so just get a couple things set here. Okay, so way back when we started, we really started with this book, if you remember, is kind of a organized a little bit different than a lot of textbooks. It's sort of the Adam's first approach, and that's sort of where we started at the beginning here. So really our beginning chapters really talked about the atom and, a lot of sort of experiments that led to the understanding of the structure of the atom. So if you remember early on, we had Thomson, and he did a lot of work with the CRT tubes, which is those cathode ray tubes, which ultimately was like a beam of negatively charged particles like electrons. And really from that, he was able to figure out sort of the charge to mass of an electron. And if you remember, followed afterwards was Millikan, who did the oil drop experiment. And he was the guy that basically took some oil droplets, sort of atomized them, using an electrical field in a chamber, and he was able to really sort of adjust sort of the electrical field in such a way that it allowed really the oil droplet just to sort of hang there. I wouldn't go up, it wouldn't go down. But basically what he was able to sort of discover, if you will, was sort of the charge on an electron. And as we talked about, sort of putting those two guys together really allowed sort of the discovery of sort of the electron, sort of the nature of an electron and properties of electrons, and obviously the mass of an electron was basically sort of came out of that. Along with that, not too long after that sort of came the early model of the atom based on sort of their knowledge that, the atom is neutral. We definitely have now discovered some electrons. We should have some type of model of the atom, which was like the plum pudding model, if you remember, sort of the early version of the atom, where basically we had positive charge sort of spread out all over sort of the sphere, and embedded inside of that sphere were these negatively charged electrons. So we had these negatively charged electrons embedded. They felt that the electron was most of the mass of the atom. So this was, again, sort of that, early version of the atom that we talked about coming out of those sort of early experiments. And it was sort of the accepted version of the atom, right, for a good period of time, until really, as we talked about, the next sort of major sort of experiment came along. And that next major experiment that came along was really Rutherford and Rutherford's gold foil experiment. So that was sort of the next sort of major breakthrough in the understanding of the atom. So we had our Rutherford's gold foil experiment. And the result of that was he basically shot those alpha particles at pieces of gold foil. And they were really surprised at the outcome of it. They expected, based off of the plum pudding model, that most of those sort of particles would go through, but there would be some deflection as it's positively charged alpha particle kind of going through a positively charged sphere. So a little bit of deflection as they would go through. And they were really surprised that what they saw was that most of them went through pretty much undeflected. And every so often one would be sort of deflected at a very large angle. So basically what that meant was the model of the atom here, the plum pudding model, was not so much the correct model of the atom. And they had to come up with, sort of a new model of the atom, which is sort of our current model of the atom. Whereas we talked about, the atom is mostly empty space. It has a very dense positive core, which is basically the nucleus. And later on, through experiments and so forth, inside the nucleus, we find that's where we find our protons, right, which are positively charged. It's also where we find our neutrons later on, like in 1930s or so there, which have no charge. And electrons are sort of on the outside. Of the nucleus. They also found that, and again, obviously some of these things weren't found through Rutherford experiment, but later on afterwards. But also, right, the other major difference was this right here, that most of the mass of the atom was the nucleus and not the electrons. And that makes sense because, as we talked about, pretty much a proton and a neutron, they're both about 1,800 times heavier than an electron, right? So an electron, remember, is about 1,800 or so times less massive than a proton or a neutron. And if you remember, a neutron is slightly larger in terms of mass than a proton if you take it out to like 4 decimal places or so. So remember that the heaviest sort of subatomic particle is the neutron, followed kind of very closely by the proton. And again, our electron is actually the lightest of them all. So that kind of brought us to sort of our current model of the atom as a result of sort of these experiments that were done. That's where we had sort of our nucleus, where we find our protons and our neutrons. Remember that most of the atom's empty space, and within that empty space is sort of where our electron cloud is. Our electrons are traveling about the nucleus at some distance. Remember, they're not traveling in pretty circles, but they are traveling pretty randomly about the nucleus at some distance. As we talked about, is sort of an overwhelming theme, right, in chemistry, is sort of that idea of opposites attract. So even though, they're out and about sort of flying around those electrons, as we talked about, there is some attraction between the nucleus, which is ultimately positively charged because of the protons being present, and those electrons which are negatively charged. And as we talked about in later chapters, that's the reason why certain electrons are involved in bonding and certain ones are not involved in bonding. That sort of attractive force to the nucleus makes a big difference on that. Any questions on that stuff there from way early on, I think, maybe the first day or so. All right. Then, we sort of got into a little bit more about the atom, a little bit more specific about the atom, some properties of the atom. Some of the things that we talked about were things like atomic number. And the atomic number, if you remember, is the number of protons that we have in an atom. Remember that that is really the definition of an atomic number. But if we do have something that is neutral, which means it has basically equals amount of positive and negative charges, the atomic number will also tell you the number of electrons because it's neutral. So all the positives and negatives cancel out. but the actual true definition of what the atomic number is only the number of protons. So although we sometimes use it to figure out electrons in a neutral sort of situation, the actual true definition of it is just that, the atomic number. We also talked about the mass number. And the mass number is the number of protons plus the number of neutrons that you have in an atom. The nice thing about these two guys here is you could use them really to figure out the number of neutrons that are present, as the number of neutrons is obviously the mass number minus the atomic number. Remember that when we look at the periodic table and we look at sort of the elements that are present there on it, on the top there is the atomic number. And remember that the bottom number is not the mass number, but this is, as we've talked about, the atomic mass. So not the mass number. Really, the only guy that you can find there on the periodic table is the atomic number. And as we also talked about, the atomic number is really important because every single element has its own atomic number, so they never repeat. So if you know the atomic number, then you know what element you're talking about. And obviously, if you know the number of protons, you already know the atomic number and also the element that is being dealt there. The reason we also know that the bottom number is not the mass number is because pretty much when you calculate the atomic number, the mass number, or you're asked how many protons, neutrons, or electrons there are, they all need to be positive whole numbers. And obviously, when you look at the periodic table, you look at the bottom, which is our atomic mass, pretty much none of them are whole numbers. They're all decimal numbers and so forth. So really important not to confuse that, as we talked about many times. You will be given obviously enough information to figure out the protons, electrons, and neutrons in these type of situations. And you should all be whole numbers. Remember that everybody has protons, electrons, and neutrons. The only one that does not have neutrons is hydrogen, right? Hydrogen pretty much has only one proton, one electron, and no neutrons. Every other element does have protons, electrons, and neutrons. And hydrogen, again, as we saw throughout the semester, has a lot of sort of special sort of properties, if you will. But it's also the only one that really doesn't have a neutron. Now, we also talked about, as we were going through here, isotopes. And isotopes are basically the same element, but different mass. And since, as we just talked about and talked about previously, the number of protons determine the element. In order for it to be the same element, it has to have the same atomic number, which means it basically has a different mass number, which ultimately means that it basically has a different number of neutrons. Since mass number is protons and protons has to stay the same. If it's the same element, then there would be the neutrons that would be different. Now, there's different ways that we can represent sort of these isotopes and elements to display sort of our mass number, atomic number. We can write Cl, for example, 27 and 17. And that's one way that we can sort of display an isotope. Remember, these numbers do have certain meanings. Here on top left is where we put our mass number, which again was our protons and neutrons. Bottom left there is where we put our atomic number. And obviously here we see nothing written, which means it has no charge. And we could use this obviously to figure out information. In this case, the number of protons would be equal to the atomic number, which would be 17. Number of electrons in this case would also be 17. Again, has no charge, which means, again, the positives and negatives need to cancel each other out. And obviously, we could use our mass number minus our atomic number to give us 10 for our number of neutrons in this particular case. So again, that's a very common way that we write these isotopes, indicating the mass number and atomic number. Another couple of different ways that, another way that we have seen it as well is something like Cl27. Remember, when it's written like this, that 27 is the mass number. And remember, sometimes you're not given the atomic number, and that's not a big issue because you can go to the periodic table, obviously, and find the atomic number, which is our number that's on top. We also talked about what happens when these things do gain charges. So if we took our Cl and it had a -1 charge and kind of the same numberage over here, again, the number of protons has to be our atomic number, which is 17. That again tells us it's chlorine, so that cannot change. So here it is the number of electrons that would change. And as we talked about, when we do get a negative charge, it means that something has gained electrons. In this case, the number of electrons that is gained is equal to the charge. So that's -1, which means this guy would have basically 18 electrons. Again, 17 positives, 18 negatives gives you that -1 sort of charge that we talked about. And obviously, in this case, since our mass number is the same, our number of neutrons would be the same thing here, 27 minus 17, which would equal 10 as well. Any questions on that stuff there? Okay. Then I believe we started getting into sort of electrons and waves sort of happening next. So there. So clearly we started talking about sort of waves and some properties of waves. So let me draw my really bad wave here. It's halfway decent, actually. So when we do have a wave, a couple of things on the wave, right, where we kind of go from peak to peak or trough to trough, that is our lambda or our wavelength. Our amplitude is sort of from the midline of the peak and down. We also talk about some things about this wave, including things like the frequency, which is abbreviated with that new symbol there, which is the frequency. Frequency, right, is basically how fast or how many times sort of a wave passes a point in like a second. Typical frequency sort of numbers, our units are our reciprocal seconds and our hertz. And remember that those things really are the same. So a reciprocal second is the same thing as a hertz. So those guys are basically a one-to-one conversion. We also talk about sort of the speed of a wave, and c is a constant, which is the speed of light. And that was our 3 times 10 to the 8 meters per second. We talked about some relationships in terms of basically these kind of symbols, if you will. The really main one was C is equal to the wavelength times the frequency. And that's sort of a main sort of formula, right, that builds off of certain things. Again, C being our speed of light, our wavelength, and our frequency. And when we think about sort of our units to typically come out of here, again, speed of light is meters per second, which means when we use wavelength here, it should be in meters. So the units cancel correctly. And then our frequency is in reciprocal seconds. And that is how we get to that. We also use this to rearrange. So you could use it to solve for the wavelength. The wavelength is the speed of light divided by the frequency. We also could solve for the frequency, which would be C divided by the wavelength. So those are 3 sort of versions of this equation that we used. We also had a pretty good conversion that we used a lot, which was nanometers, right? 1 nanometer is 10 to the -9 meters. Again, a lot of times, especially in that visible part of the spectrum, we're given wavelength in nanometers. So that's a good conversion. We also talked about the idea of the relationship between sort of the wavelength and energy. So when we have a longer wavelength, like the one kind of I drew up there on top, we have a longer frequency, and that's usually results in lower energy, and vice versa. If we have that shorter wavelength, again, one like this, maybe it's kind of occurs a much shorter wavelength. We also have a higher frequency, and usually that results in higher energy. And so that relationship in terms of energy and so forth, we saw a lot when we were talking about sort of electrons, as they sort of transition from, say, a lower energy level up to a higher energy level, they will work their way back down. And as they work their way back down, they will give off energy in the form of a photon of light that has a specific wavelength. And again, that wavelength may correspond to, maybe the visible part of the spectrum where you see color, may respond to infrared where you kind of feel heat and energy. And again, depending on sort of that wavelength, if it's longer or shorter, we will have a difference in terms of amount of energy and so forth. Any questions on those guys there? So remember that also sort of relating this to energy, that we talked about the idea of sort of quantized energy, but we could calculate the energy here using that equation there, the wavelength times the frequency. E is equal to h times the frequency here. H is Planck's constant, which was that 6.63 times 10 to the minus 34 joule seconds. Obviously, that is our frequency still. And in terms of units here, when we kind of do the equals h times the frequency, again, h is joules times seconds. Frequency is reciprocal seconds. So the seconds basically cancel out and we end up with joules as our units here. Now, we can substitute in for frequency here using this equation again, that the frequency is c divided by the wavelength, and that gives us another version of this equation that we've seen before, which is E is equal to hc over the wavelength. So this gives us really kind of two options, if you will. One option is, if you have the frequency, you can figure out the energy associated with that. And the second one gives you basically the opportunity to figure out the energy associated with a wave if you just know the wavelength. So the bottom one, all you need is the wavelengths, as the top two are constants. The other one there up on top, which is our frequency. You also have H, which is a constant as well. Remember, though, that when we do calculate the energy here, the energy can be positive or negative. And again, that's important because it does tell us, is it exothermic, which means we're given off energy, and that would be a negative number, or is it endothermic, which means it's going to be positive, going to be absorbing energy. And obviously, this depends on sort of what is happening, especially when we're talking about perhaps electrons gaining energy or losing energy. Obviously, if they are transitioning, say, an electron from a lower energy level to a higher energy level, the atom is gaining electrons, so that would be endothermic. If we're talking about an electron sort of coming back down, that would be a process where it would be exothermic. It has to give off that energy as it comes back down. We did talk about, again, that idea of quantized energy. And remember, you can kind of think of quantized energy as sort of a staircase situation where, you know, again, as we talked about, like when you walk steps, you have enough energy to be on this step or this step. You don't usually find yourself kind of between steps. And that's the same idea as we talked about sort of with energy and sort of these electrons as they move. They really do sort of gain or lose energy in these whole number multiples, which is basically represented by this equation in terms of energy, to either find themselves on one energy level or down to the next, you know, either going up to a certain energy level or going down to another energy level. They won't find themselves sort of stuck between energy levels. So they do sort of gain and lose energy in this quantized fashion that allows them to sort of completely go from one energy level to the next, whichever direction, either kind of up or down in terms of energy. Obviously, as we talked about, if they are transitioning back down and giving off energy as they do so in the form of a photon, it may fall somewhere in that electromagnetic spectrum. That we talked about, you know, on one end, we had sort of our couple of things on the way. On one end, we had like our gamma rays. You know, we had some X-rays happening, maybe some UV, maybe some visible part of the spectrum, maybe a little bit of IR happening, some microwaves, maybe some radio waves happening. And sort of the relationship here is on the kind of the right-hand side here, where radio waves is kind of our lower in energy. Which means it has a much longer wavelength, as opposed to where we come over here to sort of the gamma side, that's much higher in energy and has a much shorter wavelength, right? And this is our visible part of the spectrum here, right, where we dealt a lot with and a lot of experiments and talked a lot. And that's where we see colors, right, are sort of Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And remember that this is where we dealt a lot with those nanometers, as a lot of times the visible part of the spectrum is sort of given off in sort of nanometers. This also, the colors also had sort of that arrangement in terms of energy as well. Red being kind of the lower in energy, a little bit longer of a wavelength, and violet sort of side being higher in energy and a much shorter wavelength. So remember, as these things sort of transition, they give off something. That's where we see sort of colors happening. We also talked a little bit about the idea of, you know, elements when they're sort of heated and so forth, they give off sort of that line spectrum, as opposed to sort of a continuous spectrum that we see with heated sort of solids in the sun and so forth, where you see sort of all the wavelengths coming off in one sort of swell, kind of a rainbow sort of effect. Also, in terms of line spectrums, right, every element has its own sort of unique spectrum. And we sort of saw this happen in a couple of the early on experiments, the one where we did flame tests, where obviously when you put it into the flame, you're exciting all those electrons to higher energy levels, which we talked about. They basically want to come back down to lower energy levels. And again, as they do that, they're giving off that energy in the form of the light. Also, the kind of spectroscope experiment where we had the prism will separate out the light, where we use the the electrical discharge tubes there to excite the light bulb that had the element in it. Any questions on that stuff there? Okay, so then we also sort of got into a little bit about sort of Bohr and Bohr's model of the atom. Bohr, if you remember, sort of model of the atom is really sort of that planetary model where, you know, you have sort of your nucleus there in the middle, and then you have these sort of orbits, he called it. And basically, electrons were defined as sort of being in these orbits and going around in these sort of circular paths around the nucleus, as we sort of just talked about earlier as well. Again, not really correct in all aspects. Bohr's model works really well for hydrogen. Again, as you move away from hydrogen, it doesn't hold up very well, but it did build some of the ideas and stuff that we still sort of use. Things like n is equal to 1, n is the principal quantum number. It's basically the energy level, and that's the ground state, n equals 1. N equals 2 would be an excited state. And basically the idea of sort of those lines that we saw was basically electrons transitioning from one energy level basically to the next. That would be like n equals 1. This would be n equals 2, n equals 3, and so forth. And remember, same idea, they gain or lose enough energy to kind of travel from sort of one energy level to the next. So anything above that, again, n equals 2, 3, 4, 5, 6, 7. These are what are referred to as excited states, and they are higher in energy. And we did talk about sort of the idea of the energy associated when these electrons sort of transition, and we could calculate those by taking the change in energy is equal to minus 2.18 times 10 to the minus 18 joules. That is what is sometimes referred to as Rydberg's constant. And that was the 1 over n squared final minus 1 over n squared initial. So that's your final energy level for your electron. That's your initial energy level for your electron. And again, remember, as we talked about previously here, again, when we calculate the energy, we do want to keep the sign. So again, it could be positive or negative, depending on whether it's an exothermic or endothermic process. And when we're doing these calculations, we do want to make sure that we do keep the sign for that. Relationship as well. Again, this guy is the same as what we saw earlier. And you can basically put them all together here and solve for a wide variety of things, even in this sort of transition. You could solve for, obviously, the energy. You could also solve for the wavelength. You could solve for the frequency, kind of putting all these together. And again, as we talked about, that energy can be negative or positive, but remember, we want to then turn it to a positive number when we're calculating something like wavelength or frequency. We do not want to end up with a negative wavelength or negative frequency. So these guys here should be positive numbers. So energy, definitely leave the positive or negative because it's important to indicate that exothermic, endothermic. But if you need to carry it through to then do a calculation, for example, like rearranging this guy here and getting that the wavelength is hc divided by E, we do want to turn it then into a positive number if it's negative, so that we do get a positive number here. So that's important, again, just in terms of those signs. Any questions on that there? Another couple important ideas that we sort of talked about around in this chapter as well was really this idea of sort of throughout that chapter as well, of the dual nature of sort of light, if you will. The idea that both waves can have particle-like functions, while particles could also have wave-like functions. And one sort of guy that basically theorized about that was de Broglie, and he sort of thought of as the idea sort of standing waves where we have nodes like your guitar string. That's sort of the string is there. If you pluck it, you see the wave go, but it's kind of locked in, obviously, the string onto your guitar. Same idea with sort of the electron, and which is a particle sort of locked into sort of the nucleus of the atom, but it does still have that wave-like sort of function. And we talked about a formula that sort of describes that, which is sometimes referred to as the de Broglie wavelength, and that is the wavelength, which is in meters, is equal to h times m and times the velocity. And a couple of things here was one of the first times we sort of had this sort of unit change, especially when we're dealing with joules, and a joule equals a kilogram meter squared second squared. So again, here, if we look at the units, joules times seconds, our mass needs to be in kilograms, and our velocity here used to be in meters per second. And that's because of the joule part. The joule part, which is really, again, a kilogram meter squared second squared. And again, that's basically what the joule represents, times our seconds divided by kilograms, which is why it does not need to be in grams, but it needs to be in kilograms in this case, and meters per second. And again, that way the kilograms cancel completely. Second cancels there, second cancels there. One of the meters cancel, and we're left with obviously just a meter in this particular case. So this is the way we could kind of determine sort of the wavelength of a particle. And again, it has to do with that sort of dual nature of our particles having wave-like functions and waves having that particle-like function. We then sort of started to transition into tying sort of this quantum mechanical model as opposed to sort of that early Bohr model, the atomic model. And remember that since Bohr's model is sort of proven not to be sort of correct past hydrogen, we sort of moved into that idea of a more quantum mechanical version of what's happening really with electrons. And we talked about them no longer being sort of in orbits, electrons, but sort of being in these sort of theoretical sort of guys, which are known as orbitals. And we talked about obviously different orbitals, S, P, D, and F. And remember that every individual orbital, no matter what type of orbital it is, could hold a maximum of 2 electrons. And when we talk about these orbitals, there's different amounts of each of them. So for example, on any energy level, there's only one type of s orbital that's found. There's 3 types of p orbitals, there's 5 types of d orbitals, and 7 types of f orbitals, which means if they want to sort of max out electrons, s orbitals could hold a grand total of 2, p subshells 6, 10 for our d subshells, and 14 electrons there for our f subshells. Really sort of where these come from, and why we have, for example, 3 p orbitals in a subshell and so forth. They're really rooted in what we talked about as well, which is our quantum numbers. And there's 4 different types of quantum numbers. So our quantum numbers. There's N, L, M sub L, M sub S. And as we talked about just a second ago, N again is what is referred to as our principal quantum number. And basically what that describes is really the energy levels. And N could have values of basically 1 through 7. As we talked about earlier, N equals 1 is the ground state. It's really the lowest in energy. It's the closest to the nucleus. And followed by that, we could have L, which is the angular momentum quantum number. And basically that's sort of the shape of the orbital. I personally also call it kind of the orbital type, and what I mean by that, is it an S, a P, a D, etc. type of orbital sort of happening there. Now, L goes from 0 to n minus 1. So starting at 0, and then whatever your n value is, subtract 1 for it. It's your highest one we could go to in whole number integers going there, like 0, 1, 2, 3 type of thing. We also had M sub L. That is the magnetic quantum number. And really, for the most part, it kind of tells you how many orbitals there are. But really what it tells you is sort of the orientation in three-dimensional space, kind of in 3D space, sort of the orientation of those particular orbitals. For example, like our p orbitals, there's one on the x-axis, one on the y, one on the z, and it sort of gives you that. And our M sub L runs from negative L to 0 to positive L. Again, all whole numbers here as it goes through there. And lastly, we have our M sub S, which is our spin quantum number. And our spin quantum number is, basically our electrons in our orbitals. And remember that, when we kind of represent them, they either, kind of are upwards or down, sort of. And our M sub S can either be plus or minus 1/2. Sort of the first electron in gets that plus 1/2. Kind of the second electron in gets the minus 1/2 in terms of its orientation of its spin. Obviously, electrons have spins themselves and are affected by electrical field. Any questions on that there? Now, just sort of an example, right? For example, if we had say the n equals 2 level. So if we were on the second energy level, or n equals 2, that would give us for L a couple of options. It would start at 0, and then obviously n minus 1 is 1. So we would have an option of 0 or 1. The 0 does represent an s orbital, right? The 1 here for L represents p orbitals. And that means that for each of the L's that we have, we can do an M sub L. So the M sub L for the S would be 0. And here the M sub L would run from minus L to 0 to positive L here. And then obviously the M sub S for each of them could be plus or minus 1/2 or plus or minus 1/2 here. So if we just sort of think about sort of just drawing that little energy level, or n equals 2, what the 0 tells us is we have a s orbital, which would be a 2s orbital. There's only one sort of number here in the M sub L, which means there's really only one orbital. And we could have an electron in there that is plus 1/2, or an electron that is minus 1/2. When we go to there on the second energy level, we also have p orbitals. And if we count up these M sub L's, 1, 2, 3, that tells us we have 3 p orbitals over there. Again, really our 2p subshell. That's represented by 2px, 2py orbital, and 2pz orbital, which corresponds to those numbers just like that, -1, 0, and +1 is basically where that represents. And that's how we can specifically, obviously, if we're talking about a particular electron, really get to, individually all its 4 sort of quantum numbers based on its location. Right. So, obviously before this, if we did n equals 1, for example, if n equals 1, the only acceptable value you could have would be 1 minus 1, which is 0, which means our m sub L would be 0, and our m sub S could be plus or minus a half, which means on the first energy level, it tells us we only have obviously one orbital, and that's an s orbital, and that's a 1s orbital, and we could have an electron again plus 1/2, or an electron and minus 1/2. Any questions on that there? Remember a couple terminologies or words that sometimes confuses people. Sometimes we talk about a level or a shell. And when we're talking about, for example, on a level or a shell, it would be like the n equals 2 level or shell, and everybody that is basically contained in there would be what we would be talking about. So if we wanted to know, for example, how many electrons could we have on the n equals 2 shell or level, the answer would be 2, 4, 6, and 8. If we were talking about the n equals 1, the answer would be 2 electrons on that entire thing. Remember that there's also a sub-level or sub-shell, and that is talking about something, for example, so this guy is like n equals 2, this would be something like 2p. And if we're talking about sort of the 2p subshell or sublevel, we're talking about really just the electrons in here, right? So just those electrons in all of those 2p orbitals. And the answer would be like 6 electrons you could put in there. And that would be what would be in the subshell or sublevel. And remember, if we're talking about just an orbital, a 2p orbital, for example, again, that could be this guy, could be just this guy, or it could be this guy, any one of those individually, and those would be, again, a maximum of 2 electrons that you could put in there. Remember that, you know, if you want to sort of figure out, for example, the maximum number of electrons on a shell or level, there's actually a calculation you could do without having to necessarily draw out everything. Maximum electrons on a shell or level is 2n squared, and n squared, or n, is the principal quantum number. So for example, we just did 2 there. 2 squared would be 4. 4 times 2 is 8, and that gives us the maximum number of electrons that are there. For example, if we're on the first energy level, 1 squared is 1, 1 times 2 is 2, and that's the 2 electrons, again, to fill up that entire level. Any questions on that stuff there? Yeah. Then obviously this naturally rolled into sort of electron configuration and writing electron configuration. And obviously earlier we talked about really the different orbitals that we have, which again are S, or P, or D, and or F. Remember that there are orbitals that go after that. They just go alphabetical at that point. We really don't deal with any ones really past F in most classes that you deal with, but they do kind of go alphabetical, G, and so forth afterwards. Remember our max number of sort of electrons, 2, 6 if you fill up that subshell, 10 and 14 if you fill up those subshells along there. And there's a really order at which electrons go in, and it's a little bit different than a lot of people sort of figure. And that's because as we start to fill multiple electrons in, there's some shifting in terms of the energy levels of everybody. So for example, when there's only hydrogen involved, everybody on the second energy level, for example, every single orbital is pretty much identical in energy. So they're all the 2 S's and the 2 P's are all sort of equal across in terms of energy. As we start filling more electrons in there, there's more negative charge, there's more sort of repulsion a little bit happening, that these orbitals really start to shift in terms of their energy levels of where they're located in relationship really to sort of the nucleus as well. And we could figure out really the right order by simply recreating sort of the order by just writing basically 1s, 2s, 3s, 4s, 5s, 6s, 7s. And remember that the 1 is really the n number, so there's 7. And on the first energy level, that's where we see s's. Remember, it's not till the second energy level that we see p, so we start at 2 there, 3, 4, 5, 6, and 7. Remember, it's not until the third energy level that we see D's. So 3, 4, 5, 6, and not to the fourth energy level that we see F's, the first start up here. And this is basically our electron configuration order, pretty much to allow you to write the correct electron configuration for most things. And the major difference is, as you can see here, we go from 2p and we always start up here. We kind of zig to the end of the arrow, come back, zig back and forth. So we go 1s, then to 2s, come back to 2p, to 3s, zigzag back to 3p. And here's the major difference. We then go to 4s first because lower energy, and then zig back there to our 3d. And this will pretty much allow you, again, to write the electron configuration for pretty much anybody that you need. So, for example, if we looked at somebody like sodium, which is atomic number of 11. So remember, 11 really is the number of protons, but if it is neutral, it is also the number of electrons it would have. We would start at the top and write the electron configuration: 1s2, 2s2, 2p6, 3s1. And again, remember that it is a superscript the way you write it, not big numbers, no commas, no dashes or anything like that when you're writing electron configuration. You write it like this. We also talked about another way that you could do that, because if you look at this part of the configuration here, that is, if you count up the top numbers 2, 4, and 10 electrons, that is neon's configuration, which means you could also kind of shorthand it by putting in brackets neon, and that indicates really what I boxed there, and continuing on with the sort of electron configuration. That is sometimes what is referred to as noble gas configuration, where basically you use the noble gas that comes kind of right before whatever element you're writing for, you put it in brackets, and then you continue on with the sort of configuration there. Remember that we also talked about that we can draw what is sometimes referred to as the orbital diagram. The orbital diagram is where we kind of use boxes and arrows to sort of represent electron configuration. I won't draw it perfect in terms of energy, but for example, in the case of sodium, we would have 1s box or 1s line. We would then have a 2s box to represent the 2s orbital. And remember, when we get to our 2p here, we would need 3 boxes or 3 lines to represent our 2p orbitals. And then we would have a 3s orbital. Remember, there's kind of rules as to how we basically put in our electrons. Remember, the first one always goes upwards, second one always goes down. That is what is sometimes referred to as Paulie's exclusion rule. No 2 electrons can have the same 4 quantum numbers. Just to remind you why we cannot do that and put them both in sort of the same direction. If this was our 1s, if we did the 4 quantum numbers for this guy, this would be n is equal to 1, L is equal to 0, M sub L would be 0, and M sub S would be plus 1/2. If we did the 4 quantum numbers for this guy in the same orientation, we obviously would get the same 4 quantum numbers here. And that would be a violation of Paulie's exclusion rule. So the way that we get around it really is sort of the placement of that second electron within that orbital having a different spin. So again, now when we do it for this guy, n is equal to 1, L is equal to 0, M sub L is equal to 0, M sub S is equal to plus 1/2. And if we do it for our guy now going in the downward direction there, n would equal 1, L would equal 0, M sub L is equal to 0, and m sub s equals now minus 1/2. So that slight difference in the spin quantum number gives those electrons for different quantum numbers. They don't share the same quantum numbers, and they don't violate Paulie's exclusion rule. We follow that same sort of move here with this. We also talked about another important rule, which is when we have multiple orbitals in a subshell, they actually do go in and fill one at a time first in the upwards direction. And this is Hund's rule, which says the most stable arrangement is the to maximize the parallel spin. So when we have a situation like we do in the 1s orbital or the 2s orbital, that's what's referred to as paired spin. Parallel spin is everybody heading in the same direction. At this point, we have no option other than to basically pair them up afterwards, and then we obviously would have one more left over here. We talked about sort of the relationship between electron configuration, obviously, and quantum numbers, as we just did here. You could be very specific. And for example, if you wanted the 4 quantum numbers for the 8th electron in sodium, because of the way it goes in, we want to be careful in terms of how we count it. So obviously this would be 1, 2, 3, 4. This would be 5. This would be 6. This would be 7. And the 8th electron actually would be this guy right here. So again, you want to make sure that you're counting correctly and not put yourself over here by just going 2, 4, 6, 8. That would be not the way that it's actually filled. And if we wanted those sort of quantum numbers for that particular guy there, again, it's in the 2p orbital. That 2 is basically the n number. So we know n is equal to 2. Because n equals 2, L could have a value of 0 or 1. Remember that an L value of 0 is an s orbital. A value of 1 is a p orbital. And here we clearly see that our electron is in the p orbital, which means the only acceptable one for that electron would have to be the 1 and not the 0, because it's not in an s orbital. And our m sub L could then go from -1 to 0 to +1. Remember that it kind of goes in order. So that's -1, this would be 0, this would be +1. And we can see that the electron is hanging out there in the -1 for that. And our m sub s obviously can be plus or minus a half. In this particular case, we see the electron is going downward, which indicates that it is minus a half. So for that 8th electron, the n would be 2, the L would be 1, the m sub L would be -1, and the m sub s would be -1/2 in this particular case. Any questions on that particular case? The m sub L in terms of electron in a d orbital, you would do the same way. So for example, a d orbital has, for example, 5 of these, right? D. And basically when you would get to a d orbital, that would be an L is equal to 2, which means m sub L is -2, -1, 0, +1, and +2. And again, it kind of goes in this order as well: -2, -1, 0, +1, and +2. So again, if you just kind of filled in, if you weren't sure, you could just fill in the last part of it, or wherever you're doing for it, kind of fill your arrows in and go, okay, it's in this box, or that box. And then that's how you would assign the m sub L for that, if that's your question. Other questions on that? Or again, sort of the relationship, we did a lot of it, we went crazy. I think that's those lectures kind of doing the quantum numbers for everybody, but again, you can't get very specific obviously with those. And sometimes, drawing it, or even just drawing the, for example, if you had a question like what we just asked, you could just draw sort of the last part of it with the arrows, and that'll help you sort of identify where your quantum numbers would be. Now, in addition to obviously regular electron configuration for things with no charges, drawing the orbital diagrams, assigning obviously our quantum numbers. We talked a little bit more about electron configuration, and we talked about a couple of things. We talked about, first off, there are a lot of exceptions to the electron configuration. And the two major ones that I said you're responsible for in this class are the two ones you're usually responsible for. And that is chromium at number 24 and copper at number 29. And basically the difference is, again, if you sort of follow the zigzag sort of situation here, you would end up with argon 4s2 3d4, and again for copper, if you follow the zigzag approach, you would end up with something like this. And these guys have been found experimentally that these guys are not correct here. They're actually more stable with an extra electron in the d orbital and one less electron there in the s orbital, which means that for chromium, it would be it would be argon 4s1 3d5. So essentially what we're doing is we're sort of kind of filling a d orbital with one electron all in the parallel direction, makes it a little bit more stable. And for copper, it would be argon, also 4s1 3d10. Now, we also talked about some other exceptions to the normal electron configuration. And again, if you sort of go down the periodic table underneath those guys, actually things like silver, MO, and all those guys, they kind of have a lot of those exceptions as well. But for us, just chromium, copper is the only two you need to worry about. But again, just a reminder, again, in sort of real life, there's a ton of sort of exceptions underneath those guys in that transition metal region on the periodic table. We also talked about what happens when things lose electrons, and especially our representative elements, or lose or gain electrons, I guess is a better way of putting that. So for example, we talked about sodium a second ago, which was 11, 1s2, 2s2, 2p6, 3s1. Sodium becomes +1 charge. Again, the plus means that it lost an electron, and it lost one electron, which means it actually only has 10 electrons, which means its configuration would be 1s2, 2s2, 2p6. It would be losing this electron here. And that is also what is referred to as neon's configuration, basically. Same thing if you look at, say, something like oxygen. Oxygen with no charge is 8, which would be 1s2, 2s2, 2p4. Oxygen with a -2 means that it basically picked up a couple of electrons. Those couple of electrons will end up there, and it will end up as 1s2, 2s2, 2p6, also neon's configuration. These guys all have the same electron configuration. So sodium with a +1 charge, neon, and oxygen with a -2 charge are all what are referred to as being isoelectronic with each other, which basically means that they have the same electron configuration. Now, when we talk about representative elements, which are guys kind of to the left and to the right, not really our transition metals, but that's essentially what happens when they gain and lose electrons. When metals that are representative metals in groups 1, 2, and 3 lose electrons, they back up to the noble gas that comes right before them. When our nonmetals kind of gain electrons, they go forward to the noble gas that comes right after them. And that's, as we talked about, a really big topic of what everybody's trying to achieve is that noble gas configuration, right? So that's sort of the purpose of gaining and losing electrons. And really the basis of ionic compounds is that everybody achieves that noble gas configuration. Now, we also talked about our transition metals and when they gain and lose electrons, and it's actually a little bit different things occur in that case. So for example, if we look at iron, which is 26, and we write the electron configuration for it, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 in this particular case. Now, when the electrons go into the atom, the 4s orbital is lower than the 3d orbital. So when these kind of electrons go in, they do fill these guys up, then they start filling this guy up. Once we start putting electrons into the d orbitals, they're very close in energy to begin with, the d and the s. There's actually a switch that occurs in terms of the energy, and the 4s electrons actually end up becoming higher in energy than the 3d electrons. And this affects how something like iron or transition metals lose electrons. They always lose their s electrons first, and then they follow with their d electrons if they need to. So when we go to iron with a +2 charge, +2 means it lost 2 electrons, and that would be 24 electrons. This would get us 1s2, 2s2, 2p6, 3s2, 3p6, kind of like a D, but not so much. Try again. 3p6. And now they are actually going to lose those 2 electrons. So the 2 electrons come out of the 4s, and that leaves us 3d6. We could obviously shorthand this too. We go through here is 2, 4, 10, through up to here is 18. So we can argon it, and 3d6 in this particular case. If we went to iron with a +3 charge, it would be down to 23 electrons. Again, the same sort of format would happen. It would lose its 2 electrons here, but in this case, it now needs to lose a 3rd electron. So now it's going to come over here to our D, and we would end up with 3d5. And again, that would be argon 3d5 at that point. So transition metals are a little bit different, obviously, than sort of representative elements. They always will lose the s electrons first. Then if they need to lose more, they delve into those d electrons and start losing those. Any questions on sort of electron configuration? Yeah, so if I understand your question, so after the 3D orbital, for example, fills, you then would follow the configuration into the 4p orbital in terms of electrons. So it would follow through. There is just those exceptions. They do sort of fill, they do fill in the normal kind of zigzag way, but sort of when they are done filling, kind of completely filling on certain ones, there's just been found experimentally that they sort of transition an electron from the s orbital up to the d orbital, like in chromium and copper. Everybody else you could assume just sort of fills normally in that sort of way. But if you happen to fill up your entire sort of 3D, the next guys that would get the electrons would be the 4p would go next. Other questions on that? Okay. So then we obviously also around this time started to talk about the periodic table, obviously. So let me draw my wonderful box to represent the periodic table, I guess. We'll make it a true periodic table with a smaller box on the bottom. Looks just like your normal periodic table. So obviously we talked a lot about sort of the periodic table and sort of the different parts of it. Just to remind everybody, obviously we go with group numbers that are on top there. So we'll go like 3, 4, 5, 6, 7, and 8. And straightish, you know. There we go. All right. Just like your professional periodic table. We do our representative numbers, which is the A numbering. So remember group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. Remember that in group 1, it really does start with lithium. So for dramatic purposes, I'll put hydrogen above it. Although hydrogen is sitting there in group sort of 1 on most periodic tables, remember that hydrogen is not part of group 1. It does start with our lithium. We also got numbers that come down the other side here, which corresponds really to our sort of our quantum numbers, right? And those are our periods that go this way. So groups go down, periods go across. And I guess technically, since I wrote lithium there, that would be 2. This would be 1. All right, so not to scale, obviously, but we do have a couple of things in terms of charges. Remember, everybody in group 1 forms a +1 charge. Everybody in group 2 forms +2 charge. Really, aluminum over here is +3. We have that sort of staircase that kind of comes down, and kind of our nonmetals on top, -3, -2, and -1 heading in that direction. Remember that some of these groups have special names. So group 1, again, starting with lithium, is our alkali metals. Group 2 is our alkaline earth metals. And remember that alkaline means basic, and that's where a lot of bases sort of come from. Group 7 is our halogens. Group 8 is our noble gases. We also know that sort of kind of to the left of the staircase are metals. Kind of to upper right of our staircase is our non-metals. Remember that our staircase right here is all the way to the staircase there is our semi-metals, our metalloids. Remember, metals have shiny, they conduct electricity really well. Non-metals are dull, don't conduct electricity really well. And our metalloids really have properties that the same element is both sort of metal properties and can have some non-metal properties as well. Remember that some other things, these are our transition metals, obviously. These two sort of guys are typically on the bottom, you know, come around here, sort of in our transition metal region, and they're sometimes referred to as inner transition metals. Because if you follow the atomic numbers, they actually go through there. They're really the lanthanides and actinides, which are the 2 elements that they follow on the periodic table there at about 57 and 89 is what they would be following. We also talked about that you could really count off electron configuration from the periodic table by going through the period, because there's different blocks on the periodic table. You know, the first 2 groups here is our S block. The P block is over here in our groups 3 through 4. Here is our P block. Our D block, in terms of electron configurations, are transition metals, and our F block are down here in those inner transition metals. Remember, though, that if you are counting electron configuration off the table, you do want to be careful, especially in the transition metal region. So we'll call this the 4th period here. On the 4th period, we have our 4s1, our 4s2, but remember, Ds actually start at 3D. So this is the 3D one that comes after that. Same thing down here. This is actually at number 6. My box, so I'll put 6 here then. So this is actually 6, this is 6s. And then, you know, when we get down here, This is actually going to be 4F, the first one. So there are some differences. You want to make sure you keep track of those if you are going to count it off, but probably best to use the zigzag approach so that you don't mess anything up. But it can sort of help you out visually and stuff like that. One last thing about this that we also talked about, obviously, is why hydrogen is not part of group one. Group one is the alkali metals. Hydrogen is actually a non-metal, right? You want to make sure you remember that. Again, even though on the periodic table it's hanging out with the metals, it sometimes is thought of as having very similar sort of properties to metals sometimes, but it is technically a non-metal. That kind of goes with our guys over here. With sort of talking about generally what's on the periodic table, we also talked about sort of periodic trends, which is why we sort of see a lot of, what happens when things gain or lose electrons. So again, if we sort of draw my generic periodic table box here, maybe, there we go. So we talked about several different types of trends. First off, in general, we have atomic size. Right. So in terms of atomic size, it decreases as you go up and to the right, and it increases as you go left and down. We also talked about ionization energy. Remember, ionization energy is the energy required to remove an electron from an atom in the gas phase. And that basically means that it increases as you go to the left and it decreases as you go down. We talked about electron affinity. Electron affinity is the energy change that occurs when somebody gains an electron, and it increases in general as you go to the right and up, and decreases as you go down. And that's not to be confused with electronegativity, which is the ability of an atom to bring an electron towards itself. And that also increases as you go up and to the right, with obviously fluorine being our most electronegative, and decreases as you go down. So again, ionization energy is the energy associated with losing an electron. And that's basically what we associate with the formation of a cation, right? Which is our positively charged side. Electron affinity is the energy change when an electron is gained. And that's really the formation of an anion, which is negatively charged. Electronegativity, again, is the ability to attract an electron towards itself. So again, IE is ionization energy. And again, that's the energy required to remove an electron, basically, from an atom. Remember, in terms of ionization energy, we also talked about the idea that electrons are lost one at a time. So, for example, if we take something like magnesium, first thing that would happen is magnesium would lose one electron, and that would be what is referred to as the first ionization energy. The next thing that would happen is that guy that lost one electron would then lose a second electron, which would be the second ionization energy. And then what would happen technically is this guy would then perhaps lose a third electron. And that would be the third ionization energy. But when we look at something like magnesium and like what we talked about, magnesium is 12, which is 1s2, 2s2, 2p6, 3s2. There are two different types of electrons that we talked about. These guys are the core electrons. This is the valence electrons. So the core electrons are closer to the nucleus, they're held tighter. And what we see is as we go from the first ionization energy to the second, there's a big increase in the ionization energy. So big increase in there. There's even a gianter increase as we go this way, and a bigger increase in the amount that's required. And that's why this part doesn't usually happen, because after we lose those first two electrons, we're now into those core electrons, and they're going to be held a lot tighter. And remember, every time you lose an electron, the thing gets smaller, which means even the outer electrons are now closer to the nucleus, and they're held a lot more tighter. And that's why what we see is from the first ionization energy, when you lose the first electron to the second, there's an increase in the amount of energy required to lose that electron. And then when we try to go from like the valence electrons transition into the core electrons transition, there's a tremendous jump in the amount of energy. You might remember maybe one of them was like, I don't know, 10 times the amount of energy or 100 times the amount of energy needed to do that. And that's why in a lot of cases, we don't see it happen. We don't lose those core electrons, because at that point, all the electrons are going to be held a lot tighter, because now our positive charge is greater than our negative charge, and all the electrons have come in as we start losing electrons. So that's why magnesium stops at +2, because those are the two valence electrons. Those are easier removed than R3. So the overall trend that we see for ionization energy is it increases as you go up and to the right and decreases as you go down. Specifically speaking about the different types of ionization energy, first, second, third, and so forth, we see an increase as we go from the first ionization energy to the second to the third, and each of those represents basically losing of an electron, and it gets harder and harder to remove an electron every time you kind of pop one off. And at some point when we get into the core electrons, they don't get lost because they're so close to the nucleus at that point, and we only usually lose our valence electrons. Ultimately, what we see in all these trends here, as we talked about, is what we sort of know, that when we go up and to the right on the periodic table, that is where we have our most reactive non-metal, but these are typically our guys that are going to hang on to their electrons, want to pick up electrons. These are typically our guys that will gain electrons on this side of the periodic table. And obviously all the trends going the opposite way down here is where we find our most active metal. These are all the guys that pretty much is like, I don't want to hang on to my electron, go ahead, take my electron. Or these are the guys that typically will lose electrons. And that's why what we typically think about is metals will lose electrons and become positively charged cations, while our nonmetals will gain electrons and become negatively charged anions. Any questions on that there? Okay, so we're getting kind of to the end here of lectures. So we will stop right now, and I will go to lab.